All right, so moving along with chapter 16, we've talked about potential differences in uniform fields, but we've not yet talked about what we would do in a non-uniform field. So, for example, most of the objects we've been looking at besides a capacitor have non-uniform fields, like a point particle. All right, so we know, let's look at an easy example of a non-uniform field. So let's say we have a capacitor stacked together. So in this case, we've got an electric field pointing towards the negative plate. In this one, we have an electric field pointing in the opposite direction, and we are taking a path that's going to traverse from A all the way to B. So if you recall, delta V is equal to the electric field times the distance that is covered times displacement. However, in this case, we can see we've got two different electric fields. So how do we go after this? Well, we divide and conquer. Whenever you feel like you can't solve a problem in life or in physics, you break it into smaller solvable problems. All right, so let's find a little point at the boundary. We will call it point C, and now all of a sudden we've got two different displacements within the same electric field. So we can then calculate A to C, which is going to be delta V1, which will be E1 is equal to, let's try that again, delta V1 is equal to E1x xc minus xa, so we're just going to calculate this, and then we can do c to b. So delta v2 is equal to e2x x sub b minus x sub c, and then a to b would be equal to delta v, which is delta v1 plus delta v2. We've now converted this problem into things that we can solve. So we can flesh this out a little bit more. So this is equal to E1x xc minus xa with a distributed minus sign plus minus E2x xb minus xc. All right, and of course what this is leading to is that you can take delta V in non-uniform fields as the sum of the different field components, E sub I x plus delta xi plus E sub iy times delta yi plus, let's get that negative sign distributed, minus EZI delta ZI. So there you're just looking at all the different components of the different fields and their corresponding displacements. And of course, what this really is it's just a sum of dot products. So this is equal to the sum of the electric field dotted with the change of displacement. So this is going to be the approach that we're going to take as we look at different types of fields. Sometimes it's going to be a direct sum, and sometimes we're going to do something a little bit trickier. All right, so let's do an easy example. This is simple just to get the hang of it conceptually. So let's say that we have points A, B, and C. X equals 0, x equals 4, x equals 7. All right, and from A to B, there is a field that is 100, 0, 0. volts per meter. And then we've got a field from B to C that is equal to 200, 1,000, 0 volts per meter. And we want to look at delta V if we go from A to C. Okay, so we know that delta V is equal to minus the sum E dot dl. So delta V is equal to minus. So for the first chunk, we've got minus 100, 0, 0 volts per meter, dotted with displacement, which is just going to be 4, 0, 0. And then plus, minus, because we have that negative sign, we would have 200, 1,000, 0 volts per meter, dotted with this displacement is just 3. That's B to C. 3, 0, 0. And so delta V is equal to minus 400, 0, 0 volts, plus minus 600, 0, 0 volts. And so delta V is just minus 1,000 volts. So that's basically the process at looking at summing together a non-uniform, the delta V for a non-uniform field. So there's some interesting implications. So what this is building towards are some deeper concepts so we can understand material better. So let's revisit our conductor and equilibrium. So recall a conductor in equilibrium has a field E is equal to 0, and that drift speed is also equal to 0 as a result of having that E net is equal to 0. So, and also you can further recall when you've got a conductor in equilibrium, then you would have your applied field. And what would happen is that the negatives would go in the other direction, giving you this. Once that happens, then you get a field in the other direction. So this would be E from polarization and E applied. The magnitude of E applied equals the magnitude of E polarization. So since they're in opposite directions, then from there you get that net field is equal to 0. Okay, so given that, if we had, this is a conductor and equilibrium. So we've got distributed accordingly. Now, if we were to go from some initial place to some final place, it would not matter what path we took. Delta V for that distance is equal to 0 because E net is 0. So any path that you take within a conductor always gives you a delta V of 0. Now, what that means is V is constant. It does not mean V is 0. So does not imply V equals to 0. Might be, but we don't know. This is just delta V is 0. So you're having V minus V is equal to 0. So maybe your V's are 0. Maybe there's something else. Okay, so let's build on this and analyze a couple other interesting situation. So let's say we've got a capacitor. With large plates. So here's our capacitor. Has a gap of 4 millimeters. All right, so for this particular capacitor, we want E and the direction of E. And delta V is equal to 5 volts. Okay, so direction is really easy. It's going to go towards the negative plate, so the direction is going to be to the right. And then delta V is equal to E times S is equal to 5 volts, implies E is equal to 5 volts over 0.004 meters is equal to 1250 volts per meter. All right, so there's our electric field. It has 1,250 volts per meter in X. And now let's look at this capacitor, and we're going to insert a metal slab of 2 millimeters at the center. Here's our capacitor. Here is our metal slab. All right, so what's going to happen to this slab is it will then polarize and go to equilibrium. So this side will become minus, this side becomes plus. So then we would have Q1 plus, Q1 minus, and then Q2 minus, Q2 plus. And then these gaps here are 1 millimeter on either side. So we want to look at what's going to happen to the electric field as a result of this. So, and also E and delta V. Okay, so we know that E inside this capacitor is going to be 0, and this field will still point to the right. Okay, so first we need to deal with the charges on the new metal plates. So we know that the slab is polarized, the metal's in equilibrium, and so the net field inside the plate is, or inside the capacitor, is 0. And we can use this then to figure out what the charges are that are on the plate. So we know that the field of a capacitor is E is equal to Q over A epsilon naught, where Q is the charge of the plate and A is the area. We know that E in the metal plate is equal to 0. And so this implies that, so E1 is equal to Q over A over epsilon naught, then the magnitude must be equal to the magnitude of E2, which would be the field from the polarization, Q2 over A epsilon naught, because if you've got these two fields here that are equal in magnitude and opposite in direction, then you have a net field of 0. So the charges on the outside of the metal plate that was inserted into the capacitor must be equal to the charge of the two plates. And that enables the metal to be in equilibrium. So Q1 is equal to Q2. All right, so the effect is that the field in the air gaps is 1250 volts per meter and 0 in the metal. So air gap field, we've already calculated, it's 1250 volts per meter and 0 inside the metal. Remember, the fringe field is small, so we're going to neglect it. And we can go ahead and calculate the potential difference across all the regions. So now we're going to traverse this and go through all of the different regions. The air gaps are going to be the same, so delta V left is equal to delta V right is equal to 1250 volts per meter times 0.001 meters. This is 1.25 volts. Delta V metal is equal to 0. So delta V is equal to 1.25 volts plus 0 plus 1.25 volts. Delta V is equal to 2.50 volts. So what we can see is delta V is not a conserved quantity. So there's no conservation of potential. There's only conservation of energy, and this is a voltage potential, not potential energy. So what we're building to here is the approach for delta V in a region of varying electric field. So here are the steps we're going to take. I'll give you a hint. They look familiar. So step 1, choose a path and divide it into delta L's. So, and in doing this, you can remember delta V is path independent. But you do still need to know what the E's are for the path you're taking. And you'll see that it really won't matter which path you take. And then part of this, you want to make a drawing. Those drawings are so important. Step 2, you want to write an expression for delta V is equal to minus E dot dl of 1 piece. And step 3, add it up. Sometimes you're just going to do a straightforward addition, and sometimes you're going to use an integral. We've just seen a few examples where we've just done it numerically. So sometimes you could do VF minus VI is equal minus I to F E dot dl. So just depends. Naturally, if you're in the general class, you shall not be doing any integration. And then lastly, we need to check our results. And there's, you just want to do a sanity check. Do the units work out? Does it pass your conceptual test? So basically minus signs. Does it match a previously known correct answer? All right, so let's practice this on a point charge. I mean, we're really familiar with point charges at this point. So we have our point charge plus Q, there it is. And we're going to look at it right here. Here's our observation. All right, so if we're going to go ahead and do this observation, the first thing we want to do is we want to break this into manageable little chunks. So we know that there is a here's our initial, here is our final. So, and E1 is going in that direction, and we know that E is going to get smaller and smaller and smaller the further away we get from this point charge. So we could break this up into delta L1, delta L2, delta L3, delta L4, and then delta L5. So we have 5 even pieces. Okay, so Q is equal to 3 times 10 to the minus 9 coulombs. Our initial is 2 times 10 to the minus 3 meters from Q. And our final is equal to 8 times 10 to the minus 3 meters from Q. Okay, so step 1. We want V final minus VI. We know E is constantly changing. So we can't just do a straightforward E times S. We're going to cut it into pieces. All right, so with our 5 pieces, the length is going to be equal to 1.2 times 10 to the minus 3 meters. And we will calculate delta V equals minus E dot delta L numerically. All right, so far so good. Let's move along. So this is all in X. So let's simplify. So delta V is equal to minus E delta L, and delta L is equal to delta R. Delta V, the field of a point charge, is 1 over 4 pi epsilon naught. Q over R squared times delta R. And when you're doing slices like this, for accuracy, you want to use the midpoints. So we've got our expression for delta V of 1 slice, so that ends step 2. And step 3, we're going to add up the contributions. And for this, you simply plug in all the little delta R's and multiply this. Now, this is just a conceptual example. I think you know how to plug and chug this pretty well by now, so I'm just going to skip directly to the answer. So for 5 pieces, using this break it up approach, you would calculate the delta V being equal to minus 9.767 times 10 to the 3 volts. Now, you could make this more accurate if you wanted to use more pieces. So for example, if you use 100 pieces, then you would get minus 10.124 times 10 to the 3 volts. And then we can check our results. And we can see this is making sense. We would anticipate that it would be a minus sign. We're going in the direction of the field. So you'd expect a delta V being minus. So everything is working out so far. All right. Now, if we wanted to improve the accuracy even further, in this case, I think we can come up with an analytical solution. So in some cases, remember, divide and conquer and add up is all we've got. We can't analytically explain everything yet. That's why physics is not a dead field. So if we want to do a more precise sum, then we need to do a little bit of calculus for this shape. So you would just do integration. So for step 2, you would have VF minus VI is equal to RI to RF 1 over 4 pi epsilon naught Q over R squared dr. All right, so we can go ahead and pull out our constants. So we would have VF minus VI is equal to 1 over 4 pi epsilon naught Q RI to RF 1 over R squared dr. And so this becomes 1 over 4 pi epsilon naught times Q minus 1 over R solved from R final to R initial. And this is equal to minus Q over 4 pi epsilon naught 1 over R final minus 1 over R initial. This is the analytical expression for a point charge. Now, calculus, I could ask you to do this integral. General, this is just yours. You get to have this for a point charge. There it is, but now you know where it comes from. And so if you do this integral for our example, you would find that you would get delta V is equal to minus 10.125 times 10 to the 3, which is very similar to 100 pieces. So, potential difference along a radial path, VF minus VI is equal to delta 1 over 4 pi epsilon naught Q over R. All right, so let us do an example. We have an electron is located at the origin location C is 3.4 times 10 to the minus 8 meters from the electron, and location D is 5.6 times 10 to the minus 6 meters from the electron. And these are all in a line, so we're just going to work in one coordinate plane. And we want to know delta V from C to D. All right, so calculus, I want you to set up your integral. General, you can jump right to the solution. Delta V is equal from C to D minus E sub x dx, which is equal from 3.4 times 10 to the minus 8 meters to 5.6 times 10 to the minus 6 meters, 1 over 4 pi epsilon naught Q over x squared dx. Delta V is equal to minus 1 over 4 pi epsilon naught minus 1.6 times 10 to the minus 19 coulombs times 1 over 5.6 times 10 to the minus 6 meters minus 1 over 3.4 times 10 to the minus 8 meters. Delta V is equal to minus 0.042 volts. So in this case, as long as you know this form here, then you can just solve from there. And you'll be given some indication of whether or not I'm expecting you to set up an integral. Obviously, if you're in the general class, the answer is no. No, I am not expecting you to set up an integral. So how much work would be required to move an alpha from C to D? And we're going to assume delta K is equal to 0. All right, so moving along, delta K plus delta U is equal to work external. We've assumed that delta K is 0, so plus 2E times delta V is equal to 2 times 1.6 times 10 to the minus 19 coulombs times minus 0.042 volts is equal to 1.28 times 10 to the minus 20 joules. And so there we have brought Physics 1 now nicely into Physics 2. All right, so moving along, we can use VF minus VI equals delta V from initial to final, E dot dl, for complex paths. So, for example, we have a charged sphere which has a negative charge, radius R1, and we have a disk plus charge Q2 and we have R2 is much, much less than D. And this would have radius R2. So this is a disk like this. And R2 is much, much greater than R1. So shell disk on its side. And the shell is made of plastic. And the disk is made of glass. Okay, so we want to find here is location 1, here is location 2. We want to find delta V from 1 to 2. All right, so we have a straight line from 1 to 2. Let's set this right here so we can refer to our picture. So E net is equal to E shell plus E disk. And this is just our good old friend, the superposition principle. So we have the integral from 1 to 2 E net dot dl is equal to 1 to 2 E shell dot dl minus 1 to 2 E disk dot dl. All right, so we're going to do a quick assumption and neglect the polarization of glass and plastic. We know it will polarize, we know it's going to make a tiny field, but the point is it's a very tiny field. And the fields from the charged nature of these two objects is going to greatly outweigh that. All right, so delta V from shell is going to be the origin at the center of shell. So, and inside the shell, you will have V surface of shell minus V1 is equal to 0. And E shell is equal to 0 inside. So basically what we're doing here is we're looking from here to here is going to have one contributing factor, namely the field from the disk will be acting here. Once we get outside of it, then we would have both the field from the disk and the field from the shell. And remember, D only goes to the edge of the shell, so the total distance is actually R plus D. Okay. To the right of the shell, we have E shell is equal to 1 over 4 pi epsilon naught minus Q1 over x squared, 0, 0. And we have delta L is equal to the distance traveled just in x. All right, so V2 minus V surface is equal to R1 to R1 plus D, 1 over 4 pi epsilon naught minus Q1 over x squared dx. So this is going from here to here. 1 over 4 pi epsilon naught minus Q1 over R plus D minus Q1 over R1. And delta V due to the disk. So we can use the approximation because D is much, much less than R2. So E disk is approximately minus Q2 over pi R2 squared divided by 2 epsilon naught, 0, 0. And there's no need to integrate. Classical, you can prove this. V2 minus V1 is equal to Q2 over pi R2 squared over 2 epsilon naught times R1 plus D. And delta V due to shell and disk, V2 minus V1 is equal to 1 over 4 pi epsilon naught minus Q1 over R plus D minus Q1 over R1 plus Q2 over pi R2 squared over 2 epsilon naught R1 plus D. So as we move towards the disk, the potential increases moving opposite to the the field, exactly like we would expect.